All right, so today we're going to talk about WebAssembly. In particular, we're going to talk about CPython in WebAssembly. Who uses CPython here? Yay, who uses a different implementation of Python? Yeah, something okay. Lots of CPython people. Most of us use CPython. But in order to really understand what it means to run CPython in WebAssembly, we're going to dig a little bit more into CPython itself and how it works. And in particular, how can I write code that runs on any machine? So I have here an M1 Mac laptop, so it has a different processor to the Windows and Linux machine that I run at home. And when I run stuff in the cloud, I run stuff on Linux usually. And so I'm dealing with different operating systems and different CPU architectures. And there are two major approaches to how to make code work across platforms. The first approach, which you're all familiar with, is to use some kind of interpreter or engine like the Python interpreter. And so if I'm writing code in Python, I can write it once. And as long as I'm running it on a machine that has Python installed, or there is a Python interpreter there for me, I can run the same code anywhere, and it should just work. And so if I take a little program like this, it takes the current time, the current local time, it sort of formats that time, it writes a little message into a file called timemessage.txt, it prints to the console, and at each of these steps, it's interacting with the operating system. It needs to go through the operating system to get the current time. It needs to go through the operating system to write to a file and to write to standard out. And so we can write this code in Python, and Python is handling that for us. So we can write the code once, and even though the operating systems are different, the file systems are different, you're running it on a different machine, this code will work in all of those places. But that is because there is a different version of Python for each one of these different platforms. There's a Python compiled for Windows, there's Python compiled for Mac OS. In fact, the Mac OS one has two Pythons because there's two different CPU architectures that need to account for. And so we have, for CPython itself, it takes the other approach. Approach 2 is to have some code that you compile a different version of that code to run on each different CPU and operating system. And so we have C code, which is our Python code, CPython itself. We compile it to different executables for these different machines, which means we need to have several different versions of Python running around there. And the way that Python does this mostly is using the C standard library. You can write C code against this standard library, and as long as there's an implementation of that standard library for each operating system, you can compile CPython. So there's one set of code for CPython, and then it's compiled into different versions for different operating systems and platforms. And so both of these approaches have some drawbacks to them. Either you need to have your language-specific interpreter or engine on the machine that you're trying to run it on. Running Python code on a mobile device probably doesn't have Python installed. You'd need to bundle the interpreter with it, and then you would need to have a different version for different platforms and different operating systems because you'd have a different implementation of a different compilation of the Python interpreter. And even when you're writing code in C and compiling it for different platforms, the C standard library and the kind of different operating systems are quite different anyway. And so you need to write code like this. This is the CPython open file implementation. It has a bunch of different, right, if it's Windows, I have to do this other stuff. Oh, if this particular function is there, I do this, otherwise it's not. And so both of these approaches take a bit of work to have them work across platforms. And so this talk is largely aspirational. I have a dream one day in the future, I want to be able to write any language, not just Python. I want to be able to write whatever programming language I want. I want to be able to build it into one thing, one bundle, one package, something, and have that package work on any machine. Right? Who would like this to be the case? Yes. Right. Yes, computer Esperanto, that's a good way to put it. I want to be able to choose my language and not have to worry about, if I write Java, I have to make sure there's a JVM there. If I write JavaScript, I need to have a JavaScript engine. If I write in Rust, I need to compile different versions for every platform. I don't want to have to deal with any of that. I want it to all just work, which would be great. So I actually have a second dream as well. This is a very aspirational talk. And for my other dream, to explain this, I need to ask you all a question. Okay, we're going to do a show of hands. I need you to answer this question honestly. Do you ever run code locally that you don't really trust? Yes, okay, that's a lot of hands. I also do this. I might do something like, oh, I clone some Git repo from some random internet stranger, and then I will build and run that code. I might pip install some package I've never heard of before. What was that? Yeah, I forgot sudo. Yeah, see, I don't do that. So there's a limit to how much damage this can do if you don't use sudo. If you do use sudo, yeah, all bets are off. The bash one for running an install script, that's from the homebrew installation instructions. Just oh yeah, let's just run this script in my terminal. So I have done all of these things, right? And this is risky behavior. This is risky behavior that we all do, right? These programs don't even need sudo access to say, read the folder where your SSH keys are. Or maybe your AWS credentials are sitting in a credentials file there. Maybe you have API access tokens in your environment variables, right? You're running programs all the time where if there was malicious code in there, it could do some damage, right? So my second dream is that I want to be able to easily limit a program's access to just what it needs and nothing else. Very fine-grained permissions, yes, you can write files, but only to this folder. Or yes, you can connect to the internet, but only this particular port or this particular address. So we kind of already have this a little bit. You already run untrusted code in a reasonably secure way every day. And I'm not talking about people here who are very security conscious and run everything in a virtual machine. You all run untrusted code securely every day. How do you do that? Browsers, yes, exactly. Web browsers are great. They're basically running untrusted code machines. You go to some random URL and it's pulling all this code and just running it. And it has sandboxed that. It is secure. It is built in a way that that code can't wreak havoc on your machine. And that's really cool. But not all apps are web apps, Katie. Yes, not all apps are web apps. We want to be able to run other things, but still get those same kinds of advantages. And so if we cast your minds back to 2013, the Harlem Shake was a thing, if you remember that. Mozilla introduced, not WebAssembly, ASM.js. Who's heard of ASM.js? Yay, lots of people, that's great. It's essentially a weird subset munging of JavaScript. You could take JavaScript and label certain functions as use ASM, and that would signal to the browser that this is not normal JavaScript, this is heavily optimizable JavaScript. It doesn't use normal heap variables. It will store the heap in a byte array of its own. And it will enforce the types on various things. Essentially, it's changing JavaScript into a set of functions that can be optimized for most CPUs, that can be optimized really, really efficiently for the sort of common features that most CPUs have. Right? 32-bit integers is a lot easier than dealing with JavaScript numbers, which might be an integer, it might be a double, we don't really know until we run it. So this was able to be run extremely fast on the browser. Now, this is really ugly code. You do not want to be writing this code yourself. It was intended to be a compilation target. So we could write code in C, C++, some other language, and compile it into JavaScript, and it would run slower than it would on a normal machine, but actually reasonably fast. And this is how the first time we had CPython working in a browser worked. You could compile CPython and run it as JavaScript code in the browser, and it was maybe twice as slow as normally running it, 2 or 3 times as slow, but it was actually usable. And so if you think running Python in the browser is this new exciting thing, it's actually been done for 10 years now. But this had some downsides to it. So particularly trying to write this kind of heavily optimizable JavaScript, but still maintain backwards compatibility just in case the browser didn't have the optimizations built in, it still had to work. That is quite difficult, trying to make it fast and also compatible with JavaScript. But the bigger problem was really, really huge piles of JavaScript that you would have to download to be able to run it. Okay, so CPython wasn't super usable in this form because you had this huge download size to try and run CPython in the browser. So WebAssembly was invented. As they were sort of starting to discuss, maybe we can create some kind of compact binary format for this JavaScript code. And then once you've sort of breaking compatibility with JavaScript, you might as well like invent a whole new system anyway. So first version of WebAssembly was like built on what was learnt from ASM.js. So if you hear me say WASM and WebAssembly, those are interchangeable. That is the same thing. It's not an acronym. WASM is just short for WebAssembly. OK, so we can take code in these various different languages and compile it to a little .wasm binary file, which is a compact format. It's very fast to read and load. It's very fast startup time. And this code will run in a browser in the browser's WebAssembly engine. This is a standard across all browsers. All browsers support this now. And the binary files are way smaller than they were for ASM.js, which is great. So WebAssembly has a text format as well. You don't usually write this, because again, you just compile other code to WebAssembly, but it's used for debugging and for learning and to sort of explain what WebAssembly is actually doing under the hood. Now, this is not actually an assembly language. It is a stack-based virtual machine, right? It is its own kind of interpreter, but one that is intended to be incredibly optimizable for what most CPUs are capable of, and it's getting faster all the time as they're adding more functionality for sort of SIMD and like different CPU instructions that can be used to make things run faster and faster. In this example, this is just a little function that takes two numbers and adds them together, but you can see it's calling the console log function. And this is because in a browser, you can JavaScript can call WebAssembly functions, invoke WebAssembly scripts, and WebAssembly can call JavaScript functions if it was built to have those functions imported into WebAssembly, so they can sort of call functions back and forth. But they are separate instances. They have separate stacks, separate variables. Passing large amounts of information between the two means copying them from one to another. Okay. So back to Python. Okay. We want to make CPython work in WebAssembly. And I'm going to preface this with, part of the point of this talk is to talk about that there's more than one way to compile CPython to WebAssembly, and it means very different things in different circumstances. So we're going to go through two different ways to compile CPython to WebAssembly that are quite different to each other. The first one is compiling CPython with Emscripten. Now, if you're used to compiling things with C, you have your C file, you run GCC or something, and it gives you a binary file. Emscripten is designed to kind of drop in there, and you just say emcc instead of GCC, and it will spit out a JavaScript file and a WebAssembly file. And we're going to use this. We're going to do a live demo, and this is the Python code that we're going to run. It's the same as before. It's reading the local time, and it's writing it to a file. And the file is called time_message.txt. Okay, live demo time. So when we run CPython built with Emscripten in the browser, so the parts here that are built by Emscripten, so you take CPython and it spits out this python.js file, which is just a JavaScript sort of wrapper. That's the thing that has the API that you can call to start running Python. It has this python.wasm file, which is most of where the C code actually goes. And there's this python.data, which is essentially all the files that Python needs to be able to run in the browser, like library files and Python files that are part of the standard library go into that sort of data package here. Now, this python.worker.js and the python.html, I wrote those myself largely. I wrote the first version, someone else added it. It's in the CPython repo there as a way to kind of test out your Emscripten Python. So this is our Python code that I preloaded in there that reads the current time and writes a file. And if I run the REPL here, I can just use the REPL, like print hi. It works as a Python REPL would. The terminal itself and the text box, like that's all just normal JavaScript web app stuff. And then it's calling into the WebAssembly to run Python. Okay, so I can stop that running. And Python in this case is running in a web worker, so it's actually running in a separate thread. Okay, if I clear this and I run the Python code, it just says message written to file. Okay, we're in a browser, like where is that file? What file? Did it just write a file? Like what is going on here? And we can kind of see a little bit what's going on if we can delete this. And we can say import OS. We're importing, where is the operating system? Like, what is going on? os.list dir, if I remember that I'm typing this correctly. Oh, I need to print that. That would make sense. Run. OK, we do have a file system. There are some folders there. There's a temp home. There's also main.py, which was the code I was running before. And time_message.txt is there. So if we could say, if it was open, it's just in like the top of my root directory, I guess. Time_message.txt. Print f.read. And we run that. OK, it says the current time is 10:51. So you can tell this is a live demo. It is actually, well, it was 10:51 when I wrote the file. The string format time part isn't very like cross-platform consistent generally, so the AM/PM part didn't work. But hey, we have written a file. So what is going on with this file that we wrote? So cast your minds back to when we were talking about C, and CPython calls functions in the C standard library, and that C standard library kind of works differently on different operating systems to implement that library. In Emscripten provides a JavaScript implementation of the C standard library, among other things, but mostly that. And that implementation of the C standard library, by default, uses an in-memory file system that's in the browser. So my file system that I'm reading and writing to here is just in memory in this browser. If I refresh the tab, everything in that will be gone. Okay. So what can't WebAssembly do, at least with Emscripten running in the browser? Now, we can get random numbers, we can get the system clock time, we can do quite a lot of different operating system-y things. Reading and writing the local file system, well, it's got this in-memory file system, so you can kind of simulate that, but it's not actually my files on my local machine because browsers can't do that. Now, there is a new web API that lets you access local file systems. It pops up a thing. It gives you permission to a particular directory. But you can use that from Emscripten, but it has an async-only API because that JavaScript API is async, so you can't do synchronous file system reads and writes to that because it's asynchronous. So it's quite difficult. It is possible to access the local file system, but from CPython currently you can't. Also, sockets and networking generally aren't supported in a browser anyway, so these turn out to be mostly limitations of the browser and what you can and can't do in a browser rather than limitations of what you can and can't do with WebAssembly itself. Okay. The cool thing is, though, Emscripten does support SDL2, so you can do graphical interfaces, audio, joystick and keyboard and mouse inputs, and have that all work. And PMP-B on GitHub has done amazing work to support Pygame in the browser. So you can take Pygame games and run them in the browser because Emscripten supports SDL2, which happens to be what Pygame uses. Now, if there's a different game engine that doesn't use SDL, good luck. But Pygame happens to work. So highly recommend checking out pygame-web.github.io for a bunch of different Pygame games running in the browser there. The other shout out goes to Pyodide, which is much easier to use than trying to compile CPython to Emscripten yourself. It's packaged up. It's very easy to integrate Python into a web app using Pyodide. It actually supports installing a bunch of pip packages as well, including packages with native code, Pandas, NumPy. Lots of the data science packages will just work in a browser using Pyodide. People have made Jupyter notebooks, but entirely in the browser without needing a server. It's very cool. OK, going back to the two dreams that I had. I want to be able to write in any language, compile it once, and have it work on any machine or operating system. Sort of, yes, I guess if it's in a web browser, it works. I want to easily limit a program's access to just what it needs and nothing else. Well, also sort of. It's limited, it's safe, it's secure, but also I can't access a whole bunch of things that I might want to actually have my code access. So we're kind of halfway there. Not quite there yet. But WebAssembly was built as a web standard for browsers to use. But once it was built, and once it was standardized, once people started using it, started to think, well, WebAssembly is standardized. It's language independent. You can run basically anything on it because you can compile to it. It is cross-platform, and we have implementations of it for several different platforms already. It's sandboxed and secure, and it's pretty much it's very close to native speeds, depending on what you're doing. What if we had a standalone WebAssembly engine that we could run anywhere, including outside of a browser. Wouldn't that be cool? We could just kind of build stuff for WebAssembly and just run it anywhere. And these things exist. But you can't just kind of run WebAssembly by itself if it can't do anything like read and write the file system or access the network. It still needs to be able to do those things. And if we're going to run it everywhere, we need some kind of standardized API to be able to do those things. Hence, there is a new standard, WASI, the WebAssembly System Interface. And this is a standard that is in active development. There's currently like preview 0 and preview 1, and they're working on preview 2. But people are already using it. So I could have a WebAssembly program, and I have this API that lets me access common operating system things. It's not the same as the C API, because we don't want to deal with all the legacy things. But it kind of follows that a little bit as well. So I can read files, write files, I can get the system time, I can access the network, and it's all going through this WASI API. And so if I have, and there's an implementation of the C standard library on the WASI API. So I can use the C standard library in my normal C code, and when I build it for WebAssembly, it's built to use the WASI API underneath. Okay, so WasmTime is a standalone WebAssembly engine that supports the WASI system, the WASI interface. And so in theory, I could just kind of say WasmTime python.wasm, and I'd be able to run Python like this, and I'd be able to run whatever Python code I wanted. And this python.wasm would work on any machine as long as I have WasmTime or a different WebAssembly engine installed on that machine, which would be cool. But it doesn't work exactly as easily as this. So if I wanted to build Python for WASI, it's a little bit more complicated than building from scripting. It hasn't had as much sort of work put into making it just work out of the box and easy. It's very new. So you kind of have to say, well, I'm going to build with Clang. Clang supports WebAssembly and WASI just kind of out of the box, but you also need to provide it the sort of WASI implementation of the C library and any C, other C libraries that you want to be use. They have to be compiled to WebAssembly and then also compiled in. But what you get out is just a WASM file, right? Just python.wasm, which you can then just run on the command line with WasmTime. But if I actually run python.wasm with WasmTime like this, I get this whole giant error message that's coming out there. Can anyone tell me what's going on here? Does anyone debug this for me? I don't have my libraries, exactly, perfect. Python, so in this example, I do actually have the libraries. The libraries are there in a folder, but python.wasm cannot access those libraries. And this is because, I changed the slide and it doesn't work. So the WASI API is built with security and sandboxing in mind from the beginning. So when you're using the WASI API, there's a set of capabilities that you can grant to a WebAssembly program when you run it. If it needs to read the file system, you have to tell it, hey, you have access to read the file system, you have this directory or this specific file, you have access to that file and nothing else. If you want to read or write a particular file, you grant it access. If you want to access the network, you have to grant that as a permission to the WebAssembly program that you're running. So if we do this, we tell it, hey, this is where the Python path is, and this mapdir is saying the current directory, which is where all of my CPython code is and where all of my libraries are, should be at the root directory when I'm running in WASM. Then I can grant Python access to all the libraries that it actually needs. If you have a program that doesn't need to have access to a bunch of files, this is much easier. You don't have to do this. But for running Python, it needs to have access to the library files or it can't run. But this folder, if I have the folder with the library files and my python.wasm build of Python, I could take that and run that on any machine that has WasmTime installed. Okay? Any machine that has WasmTime or a different WebAssembly engine. So I kind of have this, right? It's early days. The standard is still under development. There's lots of things that it can't do yet, but I can write in any language. I can compile it to a WASM file or a WASM. There are also WASM Docker containers as well, which would then bundle the files in as well. And then I can run that in a way that's secure and sandboxed and limited to what it needs to be able to do on my machine and nothing else. So maybe once this becomes a little bit more streamlined, a little bit easier to use, I will be able to fulfill both of my aspirational dreams, which is very cool. So where are we at the moment? What can't WebAssembly do? So Emscripten has like a bunch of limitations, but WASI, like, it can read and write the local file system. It can do sockets and networking. I forgot to mention before, in Emscripten, you can kind of do sockets and networking, but it needs a proxy server that it opens a WebSocket to, and then the proxy server is actually handling all the network stuff. I've not managed to get this to work, even with an example for myself. I sort of managed to get it to work a little bit, but not really. It doesn't work in CPython. That part hasn't been accomplished yet. But you would need a proxy server anyway for it to run in a browser. But for WASI, it does support sockets and networking. If you're using other C libraries, especially if they're kind of operating system specific things, they're unlikely to work in WASI. SDL2 doesn't work in WASI. If you have some kind of C program that you're trying to make work in WebAssembly, have a close look at exactly what WebAssembly, the WASI API supports, and whether you need anything else for it. Sometimes you'll find, like, when we're trying to add support for zlib, and check if that worked in Python with WASI, because Python depends on zlib to do zipping, could just compile it for WASI and then link it in, and it just kind of worked, which was amazing because it doesn't need any operating system access. But if you do need to do more operating system access things, then the libraries probably explicitly have to support WASI until maybe the sort of WASI API will develop further. Okay. Where can we find WebAssembly? It's currently in use in a bunch of different places. In particular, it's used on the web. You've probably used it in websites if you visited. Figma uses it. The new Photoshop running in the browser makes quite extensive use of WebAssembly to port some of their Photoshop stuff to work in the browser as well. There's this really cool example of someone's built an entirely emulated x86 32-bit machine that runs in the browser in WebAssembly, and you can load whatever like operating system image you want onto there. So this is Windows 2000 running in my browser. That is my own beautiful artwork right there. So lots of WebAssembly is happening on the web. It's also starting to make headway into the cloud. It has potential. It's not quite in a lot of use yet. Cloudflare supports WebAssembly workers. There's a WASM Edge project. They claim that it will be potentially 100 times faster and start up 20% faster at runtime than Linux containers. I'm not entirely sure how they're making that comparison. But yes, smaller containers, because it's just your WebAssembly binary that you need, not an entire like Docker container full of Linux files for that. So there is potential for this to be huge in cloud computing, because you have this sandboxing without having to run small, lightweight virtual machines, because the sandboxing is built into the WebAssembly engine. Okay. The third one, which I'm super excited about, is sort of replacing native modules in other runtimes. So as an M1 user, I often find that Python packages don't have great support for the native compiled modules, because even though it's Python, there's some C code or something else in there that's compiled that needs to have every different platform and operating system supported. And if it doesn't support M1 Max, because they're relatively new, then I'm kind of stuck. And so this is why I'm super excited about the next talk that's coming up right now, which Jim is giving, which is about including, like, essentially, you don't need to create 27 different wheels for different platforms to have native code in a Python package, when you could include WebAssembly instead and just have one package that works everywhere. So I'm excited about that. And so you should stick around for the next talk. Thank you very much.